and this gives the allocation 0 or a small allocation, and then you write the size that you expect to be allocated. And obviously, because you have a wrap to 0 or to a very small value, then this is going to trigger a buffer overflow again. So those three very simple examples are like pillar examples of zero allocations. And we have fixed a couple of things in our software. This is not Windows specific, I must say. This is like generic. It works on Unix. It works on other operating systems. We've been working with partners to handle those things as well in our software. So this is clearly not something Windows specific. This is generic. So basically, as I said, zero allocations is a standard feature. So you're supposed to be allowed to do it. The truth is, when you do it generally, you don't know what you're doing. So it's not a new kind of vulnerability because they are allowed in the C standards. So we don't consider this a vulnerability. But just like integer overflows basically are allowed in the C standards. It's not because you have an integer overflow that you're going to have a vulnerability. Like say you have a graphical application and like you have saturation or something like that, and then there is no vulnerability because it's just intended to work like that. So in the same case, when you do a zero allocation, if you handle it like if you copy 0 bytes in a 0 allocated chunk, there is no bug, nothing happens. So this is not a new class of vulnerability, so don't panic, there is no like issue of vendor or anything. And yeah, we have done tools to detect all such vulnerabilities, at least when there is a true security issue. So we also detect when there is no true security issue, but I'm going to talk a little bit later about that. So first, like the presentation has three parts. First part, I'm going to give a couple examples of zero allocations of true bugs we have fixed in the Windows kernel. Then I'm going to explain how we have built a tool to detect all such vulnerabilities automatically in the Windows kernel. So we have removed all of them, hopefully. And then generalization of this. So sometimes you have bugs that happen in the neighborhood of 0. Say you have malloc size +1 or size +2. And so it's not a zero allocation, it's like 1 byte allocation or 2 byte allocation. But in presence of other defects, you can actually have other problems that happen in the neighborhood of 0. So I'm going to explain that this is a generalization of this kind of bugs. Any questions so far? So the very first basic code you want to do to check if you're vulnerable. So when you do a very simple dummy kernel driver on Windows, you just call the API xallocate_pull_tag, which is an exported API for allocating memory in the kernel. You just pass it 0. Sorry. Just pass it 0 here, 0 size, and then you print the pointer that was returned by this API. And what you can see is that this is not null. None of those is null. So basically on the Windows kernel, when you do malloc 0, it's going to allocate actually 16 bytes. So you are safe if you just copy 0 bytes, but if you do something different, you can have a problem. If you look at the assembly code of xallocate_pull_tag, you can see that if you pass a 0 parameter, if basically the parameter is in EDI register here, if you pass a 0 parameter, what it's going to do is just like put it to 1. And then you have a roundup, so it makes the size a little bigger, so 1 byte. So basically when you do malloc 0 or xallocate_pull_0, you have a couple of bytes that are allocated. If you do the same test on in userland application, so you have malloc, which is for C, you can see that you have the same behavior. You have heap alloc, which is for C++ applications. You also have non-null pointer. However, if you call virtual alloc, which is a low-level function in Windows that is called by both malloc and heap alloc, actually passing 0 to virtual alloc will return null, which is somehow the expected behavior, at least to me. But so if you use directly virtual alloc, that generally people are not using directly, you're supposed to use a wrapper function. You're not reliable for virtual alloc, but malloc and heap alloc are also exposed. So if you repeat that, you can see that actually there isn't, well, it's not an isolated behavior, basically. Like you can execute the same program ever and ever, and like you see that it never returns null unless you use virtual alloc. A couple of example bugs, like those are real bugs that we have patched. So they're not in the project that are released anymore, so I believe it's kind of useless to try to find them back. Well, I feel absolutely free to find them back, but I'm not sure it's going to be really useful to you. First bug. Have an untrusted data, untrusted pointer that flows here, that is passed in parameter. You probe it. So probing in the Windows kernel is like copy in user, copy to user, this kind of function in the Linux kernel. Are you guys familiar with those functions? Yeah? Anyone? Yeah? Okay. So basically when you pass pointers to the kernel, obviously before dereferencing them, you need to make sure they are valid. And you call a function called probe for read or probe for write. So you're going to make sure that you can actually use a pointer before you dereference it, or you write to it, or you read to it, or anything.